So what we talked about last time was how to solve a binary classification problem by separating with a hyperplane. In other words, you've got your two sets of points in the feature space, and there's a binary variable, which is the target, and we want to classify by that binary variable by trying to separate the two classes as best as possible. So what we saw last time were what we call linear decision boundaries. So the hard margin classifier, the soft margin classifier, and so on. So what we want to make is the following observation. So linear decision boundaries, one's coming from a hyperplane of the type we talked about, the hard margin classifier, the soft margin classifier, what we call GLM, linear discriminant analysis, etc. These are too restrictive for many classification problems. And that's simply because when we look at the feature space and we look at the data, the target classes will form groups that are highly nonlinear. Okay. So let's consider an example of how this might happen. Okay. So let's say we have points x1, x2. So we have two features, x1 and x2, in the plane. Which form two classes. So as like in the previous example, what we'll often do is our points in the feature space have coordinates coming from the features, but then the classes that we're classifying to will be indicated by like a color and or a shape. Okay, so then we can see them that way. Okay, so they form two classes that are visually, at least, well separated by a circle. Okay, so we can kind of see a separation shape. The problem with a circle, of course, is not a hyperplane. The equation for a circle is decidedly nonlinear, so it can't come from a linear equation, in other words, a hyperplane equation. But not a line. Okay, so remembering that a line is a hyperplane in two-dimensional. That's when we're talking about 2 dimensions, a line is a hyperplane. Right? Okay, so let's see an image of what I'm talking about. What do I mean when I say this? So take a look at the following picture. And ignore the middle part for now. We'll come back to it in a second. Okay. So on the left, we have our feature space. We have two features, x1 and x2, and then the two classes that we're classifying to in the binary classification are indicated in green and in orange. Okay. So if all you had was the picture on the left, if you saw that, you would immediately see that there's some kind of circle type shape, right? That does a good job of separating the green points and the orange points. Maybe not a perfect one, but probably pretty good. And that's drawn for you in the third picture. Okay. So the third picture, the one on the right, shows a particular circle that does a very good job of separating these, right? Essentially almost perfectly separates them. There's a little bit of overlap, some green ones and red and orange ones on the boundary, so it's not perfect, but it's very good, right? So if you were trying to just visually identify what's the best separation, that's what you would come up with, something like that. But how could you get to that? Okay. So this is the idea of what we're going to consider now. So an idea then to solving this issue is expand from two-dimensional space to three-dimensional space. So expand from 2D to 3D space by adding in a new feature. To the data. Okay. And here, what we're going to take as our feature take a new feature x3 given by x1 squared plus x2 squared. Okay. Okay. So the in 3D space, the points x1, x2, x3 form a paraboloid. That's the particular shape. We'll come back to the picture in a moment. Okay. And are well separated by a plane. Okay. And so a plane, of course, is a hyperplane in three-dimensional space. Okay. So going back to the image that we just saw. So the idea is, so you have x1 and x2, and we've inserted a third variable x3. So now we have our points are in feature space or in a three-dimensional space. And it's obviously not, it's hard to see, or a little harder to see, because we're drawing three-dimensional space in 2 dimensions on the screen here. But if you think about it, so the x3 is the height, you can probably get an idea that there's a plane that's almost flat that slices through that paraboloid shape, and it separates the green points that are going to be below the plane from the orange points above it. So the way we've drawn this is to try to indicate that the orange points, by and large, are higher than the green points. Okay. So there's going to be some plane that's like an almost flat plane that's going to separate those two pieces in half, cuts through it. Okay. Okay, so that's what we do. We separate the green points from the orange points in the enlarged feature space using a hyperplane. Okay. So now if we take that hyperplane in 3 space and we look at its shadow in 2 space, we project the image of the decision boundary back down into the original feature space, we get exactly what we wanted, a nonlinear decision boundary that in fact in this case looks like a circle. So that's where the third picture there is coming from. So project the resulting decision boundary back into the original 2D feature space. This results in exactly what we want. Namely, a nonlinear decision boundary that almost perfectly separates the two classes. All right, so just going back to the image one more time. So the idea is in the second picture, in the middle picture, we form a plane through the points to separate them. And then we look at the projection, in some sense, the shadow of that plane back down in the original feature space x1, x2, which is sort of like the plane in that 3 dimensions. Okay. And then what does that shadow look like? What's that projection? It's exactly the nonlinear circular decision boundary given on the right. So it produces precisely what it is we're hoping for. Okay. All right. So you might think that what we did here is extremely specific to this particular example. And how would we at all kind of manage, how could we generalize that? But in fact, the idea behind what we're using here works very generally. So this is a simple, since it's just in 2 space, and particularly nice, since it worked very well, example of what we call the kernel trick. Okay, so what's the kernel trick? We enlarge the feature space using an order called basis functions. I'm not going to completely explain the idea here. But the basic idea is, in the previous example, we identified visually that we have a circle. Okay, and then we know that kind of the equation of a circle is going to be something involving the sums of the squares of the 2 variables. Okay. Well, that seems awfully specific to that example. How would we, and if we're going into feature spaces that are more than 2 dimensions, how are we going to necessarily going to visualize them? We're not going to be able to look at it and say, oh, this is the shape that we want to use to separate. Well, so the idea is we don't actually have to do that. We'll have a given kind of a group of a set of functions, these things called basis functions, that allow us to do this enlargement in a way that will work. Okay. So in this enlarged feature space, good separation of the classes by a hyperplane is often possible. It's not necessary. It doesn't have to. It's not always possible. I mean, some data sets simply don't separate out well at all, regardless. So they're just not conducive to doing binary classification in this way. Okay, so we can't guarantee this method is going to work, but the basic idea is that it usually will. Okay. So the resulting decision boundary So if we've done good separation by a hyperplane, so the resulting decision boundary in this enlarged feature space is linear, it's coming from a hyperplane. But its projection into the original feature space may be, and often is, most of the time it will be nonlinear. You typically aren't going to get a linear decision boundary from doing this, okay? Because the linearity in the higher dimensions is not going to hold. Okay. So what's the idea behind these basis functions that we talked about? Well, we're actually going to use a slightly different term here in terms of what we're going to do. So to actually implement this process, we employ what we call kernel functions, hence the name kernel trick. Okay, so I'm going to explain some examples of these, and then I'm going to talk a little bit about the theory. Now, the actual mathematical theory behind this method is extremely deep, and if you don't know what it is, I can't draw a straight line here. All right, the last try. Okay, whatever. All right, don't panic when I start talking. I want to kind of just give an idea where this comes from. If you find it interesting, great. If not, and you have no idea what I'm talking about, that's fine. But it's just, there's a couple of observations that are worth making as we see where the kind of the high-powered theory that underlies all this. Like in particular, why does the method work, and why do we not need to do as much as we did in that simple example? So you'll see what I mean here in a minute. Okay. So two popular examples. I'm just going to give you two, but there's plenty. There's others in the text. You could also look up others online. I'm sure there's a big table of these on Wikipedia or something like that. So two popular examples of kernel functions used for support vector machines. So remember, support vector machines is the general name for this, this technique, are the following. One is to simply use a polynomial function, which is actually what we just did in the previous example, basically. We call it dth degree polynomial. So the dth degree polynomial kernel. Okay, and so what does it do? K, we'll call it K, to two data points x and x prime. Okay. So it multiplies them by some parameter lambda, or sorry, gamma, sorry. So gamma here is just what we're going to call a scale parameter. And this is a tunable hyperparameter for an actual implementation of this. And then 1 plus, and I'm going to explain this notation in a minute, angle bracket x comma x prime. So we compute something having to do with x and x prime, and then we take that to the power d, where d is the degree of the basically it's like the corresponding polynomial degree. Okay. So notice there's not actually a polynomial function given here, right? We don't write down like a polynomial at p of x equals a n x to the n plus dot dot dot, right? It's not set up that way. So we'll get to the point in a minute. So in some sense, what we just did with the circle example was like a degree 2 polynomial, right? We took square powers as the highest power involved, okay? But in that case, what we actually did is we computed the actual new feature, right? We defined a new feature x3 by x1 squared plus x2 squared. I'll explain in a minute that that's not actually what we're doing here. We're doing something easier and less computational. So the second is what's called the radial basis kernel, and this is the most common one to use, and it works. It's extremely flexible in terms of how well it works, which is nice. The radial basis is k of x comma x prime equals exp, so the natural exponential, and I'll write it in that notation in a minute, of a parameter gamma times we'll call the norm here of x1 x minus x prime squared. This double bar notation I'll explain in a moment. Okay, so it's computing something involving a difference of x and x prime. So the other way you can write this is e to the power gamma norm x minus x prime all squared. All right. So what's gamma? Gamma here likewise is a parameter, and it's related to 1 over sigma squared, where sigma is the standard deviation for a certain normal distribution. We don't have to get into the details of this right now. Okay. Okay, so there's a bunch of notation here that I need to explain. What do I mean by the angle brackets x comma x prime, and what do I mean by the double bar x minus x prime squared? Okay, so angle bracket x comma x prime is obtained by taking, so x and x prime here are elements of the feature space, so they have coordinates. Okay, so I take a coordinate, say xj of x, and the corresponding coordinate xj prime of x prime, and I multiply those together, and then I add all those up as j runs from 1 to p, where p is our usual notation for the number of features. Okay, so in each coordinate, you're taking the two coordinates together and multiplying them. Okay, and this is called an inner product. And this, in some sense, is a fancy name for a dot product. Now, when we have an inner product allows us to define a form of distance. So in other words, a size of elements. So when we write, so x minus x prime in double bars, this is given by the square root of the inner product x minus x prime with itself. So squaring it is simply an inner product. So x minus x prime comma x minus x prime. So you're taking the difference of the two coordinates, the 2 points, and you're computing this inner product expression. Okay. All right, so what's the point? An inner product on a space tells you something, roughly speaking, about the generalized geometry of that space. It tells you how different elements in the feature space relate to one another. In some sense, almost what angle are they at with respect to each other. But in higher dimensional space, that no longer makes any sense. So it's kind of a massive generalization of that idea. Okay. So when we do this, this defines, taking the differences in this way and taking their inner products, this defines what's called a distance function, telling us how far apart x and x prime are, which we call a metric sometimes, on the feature space. Which forms, then, so when you have a distance on some space coming from an inner product, then we call it an inner product space. Okay. Now, if this inner product space is nice enough, then it has a special name. So an inner product space, which is we call complete. I'm not going to define what complete means, but basically what complete means here is that when you have sequences, if you expect those sequences to converge, they actually do. And you have an inner product space which is complete in its induced metric. So this metric coming from the inner product, this is called a Hilbert space. All right. So certain types of Hilbert spaces consist of functions and are induced in a sense that I won't induced, sorry, in a sense that I won't get into. by these kernel functions. And these types of Hilbert spaces are what are called reproducing kernel Hilbert spaces. So RKHS. All right. All right. So now that I've kind of probably scared you or bewildered you or led you down some incomprehensible path of abstract mathematics, let's say, so what's the point? Okay, why am I even talking about this? Where am I going with all of this? Okay. The point is, there's in some sense to me, there's 2 points here. One of these is I'm going to say kind of whimsically, but why restrict to finite dimensions when you can work in infinitely many ones? Infinitely many. Okay. So, all right. So I'm being kind of whimsical here, but the idea is the more dimensions you have, the more room you have, the more kind of space you have to operate. And Hilbert spaces, you can form infinite dimensional ones. So these basis functions, Hilbert spaces have what's called orthonormal basis associated to them. And the idea is you have some kind of infinite collection of functions which are all orthogonal to one another and normalized, and they form a basis for the space. So you can kind of construct anything in the space out of these. Okay, so you've got kind of as much room to work with as you want. But the other really kind of important aspect of this is to enlarge the feature space, we don't have to do what we did in the example, right? We don't actually have to compute the new feature values, like the x3 values that we did in that example earlier, okay? So to enlarge the feature space, we don't need to determine the actual coordinates of points in the enlarged space. So we don't actually have to find x3 like we did earlier. Okay, we don't have to compute we don't have to go up into the new dimensional space and show where everything is. Okay. All we need to know, and this is the whole idea behind these kernel functions, are the inner products. So in other words, these dot products between the original data points, between the data points in the feature space, in the original space. So in other words, knowing how the original points relate together under this idea of an inner product is enough to basically kind of it implicitly is sort of determining how they would relate in the larger dimensional space without actually having to compute the coordinates. Okay. So it's very useful to be able to do this, because if all we're doing here when we do these inner products is a bunch of multiplications and additions, right? That's all an inner product is. So after doing that computation, the rest of it is not that hard. Okay, so the norm squared of the difference is an inner product. So it's a bunch of additions and multiplications. Okay, more of them, but yeah, it's just a bunch of easy arithmetic that a computer can do. And then you do have to do an exponential if you use the radial basis, but there's only a single exponential, right? You do this inner product of multiplications and additions, and you multiply it by some scale parameter, and then you exponentiate. There's only one exponential calculation involved. It's not like you're taking a bunch of exponentials as you go. Okay. Similarly, with the dth degree polynomial, you compute the inner product, a bunch of multiplications and additions, and you take a single big power, or whatever d is. It doesn't have to be big, but a single power. And so that's not hard either. Okay. So doing these computations of these for these kernel functions is, in some sense, computationally very straightforward. Okay. So this is computationally much less complex than having to compute all the new spatial coordinates. Okay. So the point then is really there's some high-powered mathematics underlying this whole idea. But the theory, then again, yeah, there's some high-powered stuff here. Hilbert spaces are an area of functional analysis that's quite complicated. I mean, basically, we're talking about infinite dimensional, what are called infinite dimensional topological spaces. So not easy stuff at all. But the upshot that we get from this very kind of theoretical approach is a very useful computational tool. Okay. So support vector machines. Let me write the name out one more time. So SVMs, as we abbreviate them, are the class of mathematical machine learning algorithms which use these kernel functions and the kernel trick to implement and I'm just going to put in parentheses nonlinear, because usually that's what we're interested in. If we're doing linear classification, then, I mean, well, okay. So then we're using a support vector machine, but we're using the simple example. We're using, say, like the soft margin classifier, hard margin classifier. Okay. So to implement nonlinear binary classification models. So because of this approach, they are very flexible and they are very nimble at nonlinear problems. So they're basically, in some sense, really designed for that. They are very flexible and nimble at solving problems involving complex nonlinear decision boundaries. Okay, so let's look at an example of this, where this works out very nicely in comparison with another kind of method that we already know. So we're going to look at what's called the two spirals benchmark problem. And the reason this is called a benchmark problem is the idea is that this is kind of a well-known and available data set. And so the question is, how well can a given algorithm do at this problem, right? So it's a benchmark problem in the sense that you try to solve it and come up with the best solution possible. This is like one of those sort of competition type problems you can find on Kaggle and these other sites where you can do machine learning competition and try to give a better solution than anybody else has managed. Okay. So the idea behind the two spirals benchmark problem is the following. So we generate a data set consisting of two classes, of two target classes. So binary classification problem interwoven in the form of two spirals. And then usually with some Gaussian noise. In other words, so that the spirals aren't perfect. Okay, so there's a little bit of noisiness in it. Okay. And then the question is, how well can some mathematical machine learning model, support vector machines or otherwise, separate the classes? Okay, so let's look at the two spirals benchmark problem and two solutions to it. All right. So you can see in the picture the two spirals, right? So now one of the classes are indicated. What class 1 are the red circles, and class 2 are the teal triangles. On the left, we have the solution given by a random forest. And we see that it does a decent job of actually carrying out the separation, but the resulting decision boundary is fairly ugly. Right? It has a hard time with the nonlinearity and the smoothness of the spiral. So you've got all these little kind of zigs and zags, which is kind of indicating there's probably some overfitting going on at some areas, right? It's changing a lot at various points. Okay. On the other hand, on the right, we have a support vector machine, specifically using a radial basis kernel. And it produces a beautiful, smooth decision boundary that does a great job of solving the problem, of approximating the two spirals. So let me just go back and I'll summarize this. But the idea is, not only does the support vector machine visually look better, it actually also is more accurate in terms of, if you can, of course, numerically measure how well the problem is doing in terms of classification, right? You can feed it a testing set and generate a confusion matrix of true and false positives and negatives, and the accuracy generated on the right will be better than the one on the left. So not only is it visually better, it's also mathematically better. Okay. So what we have here is a random forest, and specifically this is done using Ranger in R with defaults. Okay, so it's a good example, right, that a random forest, a default random forest, an off-the-shelf random forest, does a reasonable job solving a problem, right? Even though they didn't look great, it wasn't bad. It wasn't like a horrible attempt at solving that problem. Okay. So it does an okay job. Overall. Okay. But it has trouble with the nonlinearity and smoothness of the spirals. And in particular, it appears to overfit at various spots. Okay. On the other hand, if we look at the support vector machine, and this was using a radial basis kernel, and on assignment 5, you'll see how to implement a simple support vector machine with a radial basis kernel using a package called kernlab and then caret for training. And it's not very hard at all to implement these. One of the nice things about them is they're pretty easy to set up. And you'll see that. It's one of the shorter, easier assignments, I think, of the bunch. So this captures the smooth nonlinear decision boundary well visually. Okay. And it has better predictive accuracy than the random forest model. So not only does it look better, it actually does perform better. It's not just visually better, it's in fact, it's better as a machine learning algorithm. Okay, that's all I wanted to get through today. And then on Thursday, we'll wrap this up by talking about some extensions. So all this has been about binary classification, but we'll see it's possible to extend the support vector machine idea to multinomial classification and even to regression. So we'll talk about that, and then we'll talk about a few odds and ends just to wrap the subject up.